Okay. All right, welcome everyone. Thanks for coming. It's my pleasure to introduce Gierad Laput. So Gierad is currently a PhD student at Carnegie Mellon's Human-Computer Interaction Institute. He works with Chris Harrison of the Feature Interfaces group as well. Since coming to CMU, Gierad has published, I think, over 20 publications at top-tier conferences like CHI and WIS. He has 16 patents. He's the editor of the ACM Crossroads student magazine as well, or editor-in-chief. Let's see, if I listed all of his, I think I would take the full hour if I listed all of his press mentions. Gierad is also a graduate of the University of Michigan. He graduated with a degree in electrical engineering, and he went through the master's program as well. So he did the master's here in the School of Information, and he worked with Eitan while he was here. You were also at GSI, I think, for Mark class while you were here as well?
Yeah.
Let's see, there's anything else I missed? No? I missed a bunch, but that's mostly all I can say right now. So, yeah, next job.
All right, thanks, Steven, for the very kind introduction. So I'm here to talk about my work in the 4.5 years I've been a PhD student at CMU, and let's get to it. So we've seen this trend for quite a while now. You know, you got the big mainframe, you got the laptop getting smaller and smaller, and then until we have devices that can actually fit in our pockets. So we've seen computing capacity continue to increase while device size continues to decrease. And what this means is that we now have capable computers that are sitting on users' wrists. And actually that's a really cool thing to have. And these are also increasingly becoming more embedded into our daily lives. So we've got things that are embedded in our wrists and devices that are with us, like for example in this kitchen. And this is super exciting because these platforms bring usage scenarios that are more dynamic than ever before. Whereas you were in mainframes where you basically just have to sit there the whole time, there's not a lot of things happening. As computing moves more and more closer to humans and becomes more and more embedded into our environments, there's this a whole class of dynamic use cases that we can now have. But the critical to this success of these new computing platforms is context, and this idea is not new. Context is basically, that is implicit input, or background knowledge about the user that is vital to understanding what the user is doing. So unlike explicit input where you have the mouse and the keyboard and the touchscreen, implicit input is something that the computer tries to infer from the user. And the idea is that if you have a lot of context about the user, you could use that context to amplify the user experience. The problem is most of these exciting new devices don't actually know much about the user. For example, in this watch, even though it's sitting right here on the wrist, super close to what your hands are doing, right now it can know things like whether you're sitting, whether you're walking, whether you're standing, but so far that's about it. Similarly, you have smart appliances that are starting to become more integrated into people's homes, kind of like your Alexa, but it knows nothing about the environment. There's no idea of implicit input that would make them truly great, even though they're sitting right there in your kitchen. So it would be, one example, wouldn't it be great if as the microwave is running, you could say to Alexa, hey Alexa, can you send me a text message when it's done, right? So you're basically just saying when it's done, and Alexa implicitly knows that it knows that you're talking about the microwave or the dryer or the washing machine. That would be really cool. That would be a really cool user experience because it knows what's happening in the environment. So the point here, in my line of research, I explore opportunities for greatly enhancing context awareness in these dynamic platforms, all without costly or invasive instrumentation. And this is a hard problem because you have competing constraints. On one end, you want to increase what you can learn from the user, right? I call it like the ceiling. You can always increase the ceiling. But you want to make sure that you also don't increase the floor. What I mean by floor is like how people can adopt it. So what you want to do is increase the ceiling, but also at the same time either keep the floor or decrease the floor. And those are two different competing constraints. And in order for users to adopt your technology, it has to at least hit those types of goals. So I feel like this is the flavor of research that I do, picking these problems that allow us to increase the context without having to have costly or invasive instrumentation. And so in this presentation, I'll talk about multiple projects that makes context sensing more ubiquitous and practical and unleashing the potential of these next generation computing platforms. So my work combines novel sensing and machine learning, transforming everyday raw signals into intelligent abstractions that can power rich context-sensitive applications. So I've worked on these projects in the last 4.5 years of being a student at CMU. I've published several other HCI papers around the same time period, but I've narrowed my thesis to focus on that area. So let's start. Let's begin part one of this talk by examining how we can imbue the arm with computation. So again, today smartwatches are mostly being used as an extension of people's smartphones. So I call this the Pebble model, wherein basically right now it's just being used to like send notifications and do all these other things, like being able to discretely look at information that used to be in your smartphone, now it's on your watch. So that's what I call the Pebble model. But if you think about it, a computer on your wrist has the potential to do so much more, because unlike most computing platforms, the watch resides in your body, and it's right there. So my vision is to think of wearable devices like a smartwatch as a tool that can transform the user's arms and hands into an expressive input and sensing platform, and not just an extension of your smartphone. So I think this will truly unlock the potential of wearables. If you think of the watch as almost like ARM version 2. By wearing a watch, you get your ARM version 2. I think that would be pretty cool, as opposed to just getting a small version of your phone in your watch. Right? So one way of enhancing what you can do with your arm is actually to do things like object detection, like on-touch object detection, because lots of everyday context can be inferred in terms of what users are interacting with every day. Again, since your watch is right there next to your hand, it should be able to sense all these different practical contexts. And in this project, I'm exploiting a very particular physical phenomenon, where you can actually leverage properties like the electromagnetic emissions, or EMI, during regular object operations. So because the human body is conductive, these electrical signals actually propagate through your body, because we're just basically sacks of water. So when you touch something that is, that has EMI, your body actually absorbs it. And so if you have a sensor on your watch that can detect those EMI signals, then you can exploit all these different on-touch object detection opportunities. This is the part where I'm going to do a live demo. So hopefully everything works. Otherwise, I'm just going to show you that video. So I'm going to run. I'm wearing an M-Sense smartwatch right here with me that I built. It has all the capabilities that I'm going to show later, but I'm just going to show it to you working live. If it doesn't work, I'll just show the video. So here I'm not going to show it yet, but I'm going to show something now. Okay, so what you're seeing here is basically the electromagnetic signals that's being absorbed in my body right now. So I'm going to train this system to detect a bunch of different things, like some of the objects around me that you're seeing here right now. So let me give it like a laptop, for example. Look at the signal, what happens when I touch my laptop. You see that little spike right there? That's the EMI emission from the trackpad of my laptop. And this watch can actually detect that signal and absorb that, and I can teach the machine to learn that that is a laptop. So I'm giving it examples of what that laptop looks like. And so I'm going to go to a different one. This time it's Walter's phone. I'm going to teach it, hey, that's what a phone looks like. You see the difference between the laptop and the phone? Very, very apparent. So I'm going to teach it to say, hey, that's a phone right there. All right? And the next is too many objects. So I'm just going to go drill, which is the closest one. So look at the drill when I operate it. It also gives out this emission, right? So I'm going to train that. Tell it, hey, that's a drill. And then let's see what happens. So I'm going to press T. So right now I'm not touching any object. When I touch my laptop, you can see it can detect that it's actually a laptop, versus I'm detecting it's a phone, versus it's detecting that it's a drill. So that's my live demo. All right, back to the presentation. Also, I can keep that running if you want.
With the drill.
With the drill. And if I touch this monitor, you can see how, it doesn't accidentally cause any thing that it hasn't seen. So I'm going to close that. Actually, I closed my keynote, sorry. I'm going to quit that. Any questions so far while my slides are loading? Okay, no questions. Okay, so if you've seen in the live demo that the signals are actually quite distinctive. It turns out that every object has their own electromagnetic signature. And you can use that to basically learn the different interactions the users are doing. So here I'm using the power drill. When I touch this magnetically actuated door, you can actually see the different spikes. Different objects have these different properties. And we use machine learning to infer what these are. And so here's the process at a high level. Here's the signal, you touching the object. There's a raw signal that happens when you touch it, as you've seen. And then we compute like some form of background noise before that, and then we subtract the background noise with the actual raw signal to give you what we call like an M-sense signature, like the final output that will look like that. And you've seen that in the visualizations earlier. And so just to go through this in detail, what's happening is that the watch can absorb all those electromagnetic emissions. And so we perform some very fast sampling of these things. We perform some baseband shifting, so we're only looking at the real signals and not including the imaginary signals. And then we compute the environmental noise, and once we have those different profiles, we compute a statistical z-score and amplify the good signals and decrease the noise to give you like your M-sense signature. And once you have the signature, what you can do is use machine learning to infer all these different signatures from the objects, and you can tie all this together to have like a real-time, on-touch object detection, from a smartwatch. So that's what's happening here. And the types of objects you can see at home, there's like just a ton of them that emit EMI. So schedule display, different types of laptop. That's a large touchscreen right there, like an iPad. A fridge. All these different things emit EMI, and we can use that and learn all the types of objects that you're interacting with. And it's not only limited to things. You can have like your motorcycle. They also emit EMI, or even static objects. Does anyone have an idea why this right here, like a static ladder, is emitting EMI? Anybody have any clues on why that's happening? So basically, the ladder is kind of like an antenna. It functions like an antenna. It absorbs all the EMI in its environment, like AM noise or even like the EMI from the fluorescent lights. So it turns out that even though the object is not electrical, as long as it has this capability to absorb some of those EMI, you can actually detect those too. Okay, so we ran an evaluation on like how well does M-sense work. And so we want to see like how accurate and robust is the sensing system, how consistent are the EMI signals over time, how unique are the EM signatures across a wide range of objects, right? So these are like questions that we tried to probe in. So I'm going to let you go through a series of studies that we did. So the first one is accuracy and longitudinal consistency. So we got one participant, and then we trained that participant, make them like touch different objects and captured all that data. So here's the list of objects that participant gathered and collected. 6 weeks after that data collection, we recruited 12 different people with different physical body characteristics, because it turns out that different people's BMIs absorb different types of, they can affect the signal. So this was done in 2 locations. So remember, the setup here is that one person collected data. 6 weeks after, 12 people tried to test on that data. And here's the study results. From 9 objects across 2 locations trained on one person, we can get an accuracy about 96.1%. So that gives you a really good sense of like, hey, the signatures are unique, and B, the signatures are consistent across time. And that's a really good result. So the next thing we did, okay, how discriminative are these signals? So if you could do 9 and consistent over time, can we expand that list? So we went through 24 objects spanning different categories. And these are the types of objects you see, and you can see the different signatures are really, really unique. And it turns out that, these signatures can be, you can distinguish these signatures at an average accuracy of about 97.9% across 24 objects. And that's what the confusion matrix looks like. So a lot of them achieve 100%, but there's also a little bit of confusion in some areas, but overall it's about 97.9%. The third question we want to ask is, what about the EM signatures of like similar category objects, similar refrigerators or similar laptops, similar LCD devices? It turns out that these guys have unique signatures too. So even though we tested on 2 refrigerators, there was 0 confusion between the 2 refrigerators. Same thing with the laptops. 0 confusion with 2 laptops. 4 LCD devices, 0 confusion. There was a little bit of confusion with the 2 lamps, but it's only around 1%. So even though they're similar classes of objects, they still emit a different EMI signature. What about identical objects? So would identical objects produce similar EMI signals? So we looked at 5 iMacs and 4 conference room schedulers, and I was able to identify 100% that they are similar devices. The same with the other class of devices. So what this is saying is that an iMac built on like 2011 will emit the same signature for the same iMac built on that same year. It makes sense. And a different iMac that has different electrical components will emit a different signature because they're made differently. There's a lot of takeaways that you can extract from that. And I'm happy to answer questions offline to figure out like what kinds of user experience you could use once you're able to A, identify different types of iMacs, or B, identify same classes of iMacs. So those are just examples. And you can actually build object libraries if you have this like repository of like EMI signatures. So you'll have large collection of EM signatures. It can be indexed and queried. You can detect unknown objects once you have this large repository. And the other cool thing about this is that it doesn't have to be through your hand. Like what I said, we are sacks of water. So if I'm stepping on a Fitbit here. It's through my feet, but then the watch can still absorb that signal. I should have shown this demo earlier, but if I put my nose into my laptop, the electrical signal absorbs my body, the watch can still sense it. So there's some cool effects here that you can extract, and some robustness there that transfers over. Okay, so what is this going to be useful for? So I'm just going to let you go through quickly what this can be useful for. So, for example, if you have your watch can know that you're brushing your teeth, it can pull up like a timer and say, hey, you need 60 seconds to complete brushing your teeth. So you have like a little timer. Again, like using context to enhance like new types of experiences. Also, if the system knows that you're stepping on your weighing scale, it should pull up like your history, basically. And if the watch knows that you're turning on the refrigerator or using the refrigerator and turning on the stove at 8 a.m. in the morning, then it can infer that, hey, you must be making breakfast, so you know what? I'll play you NPR or something like that. Right, so these are just the types of like predictive experiences that you could use once you have this capability. All right, MSense is great, but the classes of objects it can detect is still narrow. Like it has to be, electromechanical. It has to emit some electromagnetic noise. But lots of objects don't emit EMI noise because they're well designed and they're shielded properly, right? So it turns out that a flip side to this is that most object interactions are really static. They move a lot. So if I'm using this drill, it's not only emitting EMI, but it's also emitting vibrations, right? So you can actually exploit that capability. With Viband, I further enhance context awareness by using the micro vibrations that your hand experiences. So I'm going to tell you how this is done. So basically, all modern smartwatches contain accelerometers. But their APIs generally limit the accelerometers to 100 hertz. And that's sufficient for detecting things whether my hand is up or down, or whether I'm walking or running. Very, very basic. But it turns out that existing accelerometers in your watches can be tweaked into this rarely used high-speed mode. By modifying the kernel and writing a custom driver, we can enhance from 100 hertz to 4,000 hertz. There's lots of cool things you can do once you have this ability to detect micro vibrations. So once you have that, there's some cool stuff. So I'm going to show you an example. So look at the video here. There's 3 different lines. The first one is 100 hertz accelerometer. The second line is 4,000 hertz accelerometer. And the third line is just a microphone. So when I turn on the toothbrush, you can see that the top one is just a straight line. But the middle one at 4,000 hertz has this, really unique sine wave. The microphone is just noisy, right? So even if I'm not touching the toothbrush, the microphone is still like emitted. But the accelerometer only triggers when you're touching it. So that's a really cool property because now you're robust to noise. But the point I'm making here is that at 4,000 hertz, there's lots of things you can detect. And so it turns out that to implement this, you actually don't have to do much because the accelerometer is already there in the watches. So you basically just have to go through like the data sheet and just tweak some parameters. And it's a software-only solution. And the cool thing about this is, unlike MSense, which is a hardware solution, Viband is software-only. So you can technically deploy Viband right now as an over-the-air software update. And I think that's pretty cool. So what's happening here is I'm using the same pipeline. You get your accelerometer data, sample it at high speed. You can fuse this signal so that you're orientation independent. You apply FFT processing and windowing, and then feed that into a feature extractor, and then machine learning to power applications. So I'm going to show you 3 example domains that Viband applies to. So first is gestures. It turns out that once you can detect micro vibrations, you can detect very nuanced things like tapping on your skin, clapping, and doing all these different things. Right? So here I'm tapping the band, I'm tapping the palm, I'm tapping all these different things. And also you can detect one-handed gestures like pinch, snap, rubbing, flapping up and down. And you could use those to power up things. You could use 2 hands. You can bump. This is my favorite right here, making it rain. So you can do all those different things, right? and the cool thing is that if you look at the signatures, they're super unique. And then you can have a level of abstraction where you can use this as UI elements. So you have buttons, you got sliders when you have this. You can have things like radial knobs, so you can do these gestures and then do knobs based just on that abstraction. So you can have counters just by rubbing. And you could do things like navigating like Netflix or something like that. Or you could do like 3D positional tracking like that. So there's lots of cool things in the gesture realm that Viband enables. And of course, because things around you also emit micro vibrations, you can use Viband to detect objects. So here, you can look at the signature, and it's very unique. The micro vibrations for each of these objects are super unique that you can use them to identify and ID different objects, right? Like passive objects that are not electromechanical, turns out that the serrations in those saws can be used as a signature, right? Vacuuming, like all these different things, like a nail gun. Just look at the signature; they're super unique and they can be distinguishable. So there's a lot of these things. I'm not going to bore you with all the different objects that vibrate because there's a lot of them. And the thing is, once you know that you can sense vibrations, you can also send data through vibrations, which is actually quite cool. So what I did was, if you have a transducer, something like that you can buy on SparkFun, you can make that transducer vibrate in a very particular way. So you can use like frequency shift keying to basically send data from the actuator through your finger and to the smartwatch. It's like direct coupling. It's like the data flowing through your arm. It's like, how cool is that, right? So you can do things like that where you can use that as a way to bootstrap data sending. So it kind of like it's somewhat secure, I guess, because it's just physically flowing there. And I think that enables a lot of cool things. I'm going to go through quickly about the evaluation here. It's kind of like the same model as what I did with MSense, but we still want to know whether how accurate is this. So, recruited users, 17 users, and we tracked their BMI. So what we tried to address here is those 3 application domains. Can we actually validate them? So for gesture recognition, we have all these different gestures that we try to let users perform, and you can see the different signatures. These are very different, and across all these different gestures, we can actually get an average accuracy of 94.3% just by detecting these different gesture classes. Okay, so for object detection, we gave users 27 different types of objects across different locations. Again, trained on 1 person, and then 4 weeks later, we take that training data and tested it on the users. And then we also did things like, what if you remove the watch and put it back in? Would that actually affect, the accuracy? And these are different objects and their vibration signatures that you can see. And it turns out that you can detect, at a very high accuracy, the different types of objects. As you can see, the signals were really, really unique. And it turns out this was surprising, there's no significant difference between different types of watches. So what I forgot to mention was we also used 2 identical watches and see if there's a difference between those signals. It turns out there's no difference between those watches, and there's no significant difference when you take the watch and put it back again, which is a very positive result for robustness. And here's what that confusion matrix looks like. So we can detect objects of around 94%. We also wanted to know if the system can detect false positives, right? Because you want to be robust. So if we ask users to perform rigorous activities, like walking for 2 minutes, doing jumping jacks, and washing their hands, to assess whether false positives are going to get triggered. It turns out that it actually only generated a total of 6 false positives within those activities that the user did. But the clever thing we did here is you have to train the system to learn all these other things that you can call like a background noise. And once it has a good set of these negative background noise, it can be more robust to false positives. And you can see the robustness here in this demo where I can successfully detect that even if I shake my hand, no triggers happen. Right? Okay, and take a little bit of a breather. So let's go to some example applications of what you can do. So of course, once you have that, you can basically enhance, you can use your skin or your, the area around the watch as an input. This is a little bit dark, but let's say the lights are off, and then you flick, and then you turn on the light, right? And then you can do this gesture where you're actually controlling the dimness of the light, analog fashion, and you can like flick to commit that setting. Also, when you're lazy, clap your hands instead of turning on the light, you turn on the TV, and then you can navigate through different remote devices using the watch. And then, you can flick to like confirm. If you have like a recipe type of an application, right? I turn on the egg beater, and you can see, oh, it knows what your progress is. It knows that you got to keep mixing, right? And then if you stop mixing, it's like, oh, it stopped. The progress stops, and then it says, hey, you got to keep doing this. Your egg is not yet done. Turns out also in a guitar example, you can use this to actually tune the guitar because you can know the actual vibrations, the reverberations of the guitar. You can use that to actually tune it. So you're like tuning through coupling, which is actually a pretty cool deal. Right, and you can see, okay, you're this off, you're this much off, and then, now your guitar is tuned, you can play some cool music. This is also one of my cool favorite examples. So you can have a Nerf gun. You can actually detect different modes of the Nerf gun, right? So when you're reloading or shooting, you can see the bullets in there. It's like, oh, you got, one more bullet left, and then it's time to run. It's low ammo, and then you go, right? So here, the takeaway here is that we are now inputting digital experiences to analog objects, like objects that we never think of as being digital. With this technology, you are now able to supply that, bringing them to the digital realm. So here's an example of the vibrations, basically what we call structured vibrations that you're sending to the user. So if you embed this in objects, the objects can transmit information such as the temperature of the glue gun, or whether the contact details of the professor, like this one. Okay, so I've shown you 2 projects that imbues the arm with computation. And again, my vision here is to transform the arm into an input and sensing platform. Not just an extension of your smartphone, but basically ARM version 2.0, just by wearing a watch. However, in some cases, user instrumentation, like wearing a wearable, can create steep requirements, because you actually force people to wear watches, right? So, for example, if you're in a classroom, you want to create a smart classroom, you can't really assume that all students will wear watches, right? So, what do you do then in that situation? So, in this case, part 2 is what if you instrument the environment instead of instrumenting users? So I call this a complementary approach, which is, again, to embed sensors at key probe points within an environment, leading us to the notion of computationally enhanced environments. So my motivation for tackling this space is that these smart environments have been explored have been sought after for quite a while. Lots of people have worked hard on trying to realize this goal. Today, these efforts might fall under the smart home, right? Or other people call it the Internet of Things. But regardless of these different names, the goals have basically remained the same over decades. That is, you apply sensing and computation to enhance, the environment, especially as it pertains to physical spaces, right? And with this type of data, there's lots of things you can learn, right? But the problem is, right now, how we're thinking about this space is that there's 2 ways. Usually, you buy a smart appliance. You buy a smart fridge, a smart faucet, smart dishwasher, smart microwave, etc. These cost money, and also these guys are made by very respected siloed manufacturers, and these devices don't actually talk together. The other approach is you just put a bunch of sensors in your space, right? These are cheap. You can buy them at SparkFun. You can have all these different things. The problem with this is that they're ugly because you have things everywhere, and then you have to manage like battery life, etc. Then the smart home, the vision of the smart home is mostly just changing batteries, right? So we don't want that too. So my vision is like, can we take all of that and like plop that into one sensor? Is that even possible? Is that right? So I call this when Neo in the Matrix does this thing where he realizes that he's the chosen one. He creates this Matrix bubble effect. So I'm not sure if you guys caught that, but that's kind of like what I'm trying to do here, right? So is it actually possible to merge all that into one device? So that's the core of this part 2 of this research thread. Okay. So I've explored this space and actually created a taxonomy of what I call the sensor utility taxonomy. So on one axis, you've got the number of sensors. How many number of sensors do you need to instrument a place? And the number of sense facets. Like what types of things can you sense, right? And let me walk you through this taxonomy, because there's lots of people who have done really great work in this space. So the first area that I want to look at is what I call special purpose sensors. So you're in the one sensor, and you can sense one thing. So things like, sensing, putting tags in your faucet, being able to sense water usage, door sensors, you put things in your door, being able to sense whether the door is opened or closed. So I call that special purpose sensors. And because they're one-to-one, they're in the lower left of this taxonomy. The second part is what I call distributed sensing systems. So you have many sensors. They can also sense lots of different things. So that's why they occupy the right half of this space, because you can basically densely instrument spaces in this fashion. So there's lots of different work in here, like sensor networks and home security sensing and many more. But what you really want is, you don't want to have lots of sensing instrumentation. You want few, but then have lots of capability. So I call this infrastructure mediated sensing, because lots of people have done work in this space where you basically probe specific points in the infrastructure to detect whether the water usage in your house or the electrical usage in your house, and they're usually just probing one point in the environment. And the constraint here is that because they can sense you probe point in one area, but then the types of facets that you can sense is also only in a limited class. So for, let's say, detecting whether water plumbing is being used, you can't really detect whether the microwave is on or the washer is on or not, because it's not tuned to that particular facet, right? So that's why it's under the one to few part in this taxonomy. So what's really challenging is this idea of general purpose sensing, where you have one sensor that can sense many. So this was the vision that I proposed earlier. So how do you actually do that? So I feel like computer vision is the closest to being able to achieve this goal. So however, cameras have been widely recognized for their high level of privacy invasion, and so it carries some deep stigma, but how can we probe and get this notion of general purpose sensing with just one device? So I'm going to show you two projects in this space. First is Zensors. So Zensors was a project done at CMU, and with Michael, working with Walter on this project, and a bunch of other people, Robert, Jason, and Chris, and Jeff. So the idea here is that, what if you can repurpose a camera sensor to achieve a notion of general purpose sensing? So here I put a phone, and then it's facing the parking lot, and so I have a view of the parking lot. So I highlight a region of that parking lot, and I ask a natural language question like, how many cars are in this parking lot, for example. And so now I have a context that is driven by my question, and it's based on an optical feed. And I specify how long I want this feed to be. And then now, there it is. You have a sensor that can ask, how many cars are in this parking lot? And then we got lucky because there was an actual car that moved. So we could actually see like the data changing. So just within a couple seconds or even a minute, you could actually see answers to your questions like right away. So it's a pretty cool and very versatile type of sensing where we're combining computer vision and behind the scenes crowdsourcing to actually give you this natural language type of sensor feed, like right from the get-go. Of course, that was just like a phone, a repurposed phone, but you could use other types of cameras and you can ask lots of different questions. Is there a car in the handicap spot? Or is the crowd gathering in a specific corner? How many people are falling asleep in this talk? You know, all these different things. So again, you can have all these different questions. So if you're a business, you can have, you know, a sensors device, and then you can ask lots of questions. For example, you know, how many glasses need a refill? Or if you're in an industrial setting, are there at least 2 people in the room, or what equipment is being used? So let me show you like how sensors work. So in this case, when you put in sensors, it asks the crowd for an answer to that question you just gave. And so by, you know, at the get-go of minute 1, you get answers from the crowd right away. So, you know, how many cars in the parking lot? And that's human intelligent answer, so a specific level of accuracy. Behind the scenes, we trained a machine learning algorithm to learn the different, basically you're training a machine learning algorithm behind the scenes as it tries to catch up with the labels from the crowd. And once it gets to a point where the human accuracy and the machine learning accuracy are almost the same, or you know, comparable, we can switch automatically. So initially it's bootstrapped by the crowd, and then once the machine learning picks it up, we can switch and it becomes a fully machine learning operation. So that's a pretty cool concept actually. But what happens if, you know, there's a snowfall that comes in, right? The machine has never seen that data, so the machine learning algorithm would tank down. And so that's the part where you need to periodically assess how well your sensor is doing. But when that happens, we switch back to the crowd, and then we can add the snowfall data and bootstrap your machine learning with that new data. And then this process keeps going. So now you have this platform where you can actually ask real-time questions to real-time queries that you have, and you get like data analytics from the get-go. And the cool thing here is that you actually only see as a user like the top part. The accuracy is always like either on par or equal to like human intelligent answers. So it's a very, very nimble system that gives you this flexibility to basically ask lots of different questions using a camera feed. And I'm going to talk a little bit more about like some future work in this area, but because of the constraint of time, I'm just going to move on to the other project. But the point here is that we try to address general purpose sensing through computer vision means, right? But again, while these CV-based sensing approaches are powerful, cameras have been widely studied and recognized for their high level of privacy invasion and social intrusiveness. And you know, so can we replicate sensors but without the camera? Is that even possible? Can we do that? So we surveyed a bunch of different sensors used in commercial and academic systems, and you know, there's a ton of different types of sensors here. And what we did with our system is that we tried to we tried to extract all of the different facets that you can sense from all these different research and commercial work, and then take all of those sensors together, but without the camera. So what happens if you have that device? So this is the device right here that you're seeing. So we took all of those sense facets, we put them into like one enclosure, and see what we could do with it. Like, it can be a tool for us to figure out whether we can actually do general purpose sensing, right? And so this is how it works. You have this board, you plug it in to your environment like that. It's super straightforward. Because it does not rely on like batteries, it can do really heavy computation just from the board itself. But then you have to find a socket. But that is the constraint that we're trying to address here. So this is how it works. You just plug it in, and then the idea is that once you plug this in, you turn a space into a smart space. So let me show you what the data looks like. So the smart sensor is over there, right there. When I turn on the faucet, you can see that the accelerometer at the top is being activated. And when you do things like turn on the garbage disposal, you can actually see, you know, the different signals being activated. Same with the blender. You can see, if you look at the acoustic signal in the blender, when you turn it on, it gets activated. So basically, you have all these different physical phenomena happening in your environment. And with this one sensor board, you can actually digitize that entire space, right? And if you look at when you turn on the stove, you can actually see like that little dot is actually like a heat sensor. Actually, let me recap what's in the board, just so you guys get some grounding again on what what's happening. So I think I went too fast. So in this board, there's a bunch of different, no camera. So there's an accelerometer, there is a microphone, there is a magnetometer, barometer, directional heat, etc. And that's why you can digitize all these different spaces, because you have all these physical properties you can sense from one sensor board. Okay, let's go back. So once you have that, there's actually lots of things you can figure out. So if you have a temperature sensor, you can actually detect when the water is boiling just by looking at the heat, right? You can detect whether the AC is on or not by, again, still looking at that temperature. AC is on. When it's on, the temperature drops down. When it's off, it tries to rise back again. So those types of phenomena you can happen, or you can extract. You can use the color sensor to detect whether, what state the 3D printer is on. So just by looking at the LED lights of the 3D printer, you can detect whether the bed is heating, the extruder is complete, or when the printer is beginning. Same deal, you can detect light patterns during the day once you have these color sensors. So my point here is that you have these raw sensor streams. And with raw sensor streams, you can abstract that raw sensor stream so you can get this notion of what I call a synthetic sensor. Like, based on these raw signals, you can create almost like a virtual sensor that you can ask from this device. So I'm going to show you what I mean by these synthetic sensors. So basically, based on those raw signals, you can train a faucet running sensor, or a garbage disposal running sensor, or a blender running sensor. You can detect all these different things just from this one device. So again, instead of instrumenting the environment with many sensors, you can just try and detect that from one sensing point. Right, so as you can see, we can detect all these different events just from this one guy. So the idea is that you plug this in, you turn this space into a smart space right away, just with this little tiny package. And if you extend this in other domains, turns out you plug this in your bathroom, you can detect whether the faucet is on, or whether the right faucet is on, or the left faucet is on, whether the blow dryer is on, all these different things. Whether the toilet is flushed, right? Now I made my kitchen a smart kitchen just by plugging this guy in. That's super cool. Again, you can detect all these things like, that the fireplace is lit. So now you have like a digital fireplace sensor. You can detect whether the dryer is running, the HVAC is running. Again, all different facets in your house that emit all these physical properties, and we can pick that up and learn from it. So when you're like in a workshop environment, you can detect which machinery is running. Whether exhausts are running for safety, or like heavy equipment or dangerous equipment, you can detect all these things. You can also detect things in your office, whether someone is knocking or not, whether the door is closed or not, whether the phone is ringing. Actually, we can also detect whether you're writing on the whiteboard or when you're erasing. Right? Those emit different signals. We can digitize those and take those out. Oh, water running too. And also when you're flushing, all these different things you can detect. So what I call these first order synthetic sensors because they're basically all about like actuation, whether it's on or not, right? But you can have a level of abstraction above that to be able to get a sense of other more clever things. For example, and I call this second order synthetic sensor. For example, you can use the faucet activation or the paper towel activation to count the number of sensors. You have this property now based on the activation, which you have an abstraction called count. So now you can count the number of paper towels that's being used, right? So you can have facilities basically digitized, whether you need a refill here. So here, saying paper towel is low, so you send facility sends an email, right? That's pretty cool. So here you can measure the amount of water that's being used. So you put the sensor in your home, you can actually get a sense of how much water is being used, and you can compete with your neighbors and say, hey, Walter's wasting a lot of water compared to like this other guy. So you can use that to have these other levels of abstraction. So here, it's about duration. How long the thing has been on gives you a sense of volume. We can also detect states. So we can detect all these different events happening in the microwave, whether it's open or closed, whether it's running or whether it's like stopped, right? And you can build a state machine out of these activations. So you can follow the state machine over there. So the door is open, you close it, it moves to the next state. It's like available. You turn it on, it goes to the state that's in use, and then you speed it up, blah blah blah, and then it knows that it's finished because it heard the chime. So it's tracking that it's finished, and then you open it again, close it, and then it follows this. Basically, based on these activations, you know the state of the microwave. And so you can imagine building more and more on top of these different abstractions. You can go from second order to like nth order synthetic sensors by just combining all these different properties. So that's it for this part. And hopefully I've shown you two different domains. One is like you imbue the arm with computation to basically enhance context awareness. Second is you instrument the environment to give you a lot more context awareness without having to burden users with wearing something. And I believe that by having these two, we actually are increasing the ceiling of what you can do, but also making it so that the adoption is not that great by using form factors or choosing installation types that are either just one point or just on the body. So very, very easy to adopt. So let me talk about future work here really quickly. So right now, I focus on these things in this talk, but I'm currently working to follow up on those threads, basically to deploy these things in the wild. So what if so right now we're running a study where we're making 50 users wear the Viband smartwatch and see if we can detect different activities. I'm going to show that some cool data from that earlier. We're deploying sensors to I think 50 homes right now at the moment to get a sense of like what types of questions people would use and the performance of the system. For the synthetic sensors, we've deployed that across 3 locations, 10 rooms, and get a sense of like what if the sensors work together. So I'm just going to show you a little bit of a run through of what this future work would look like. So I'm collaborating with UPMC right now in Pittsburgh to actually sense if we can have all these different fine-grained activities. And right now we're working on trying to figure out whether if you let kids with ADHD wear this, whether there's a difference between, you can diagnose just by letting them wear a watch, whether there's a difference between ADHD and a kid with no ADHD. Because right now the way for people to actually determine this is just basically diaries. So if you have like a Viband technology that can detect fine-grained hand activities, for example, you can extract all these different types of clinical questions. So here I'm detecting different types of fine-grained activity. These are different from gestures. These are like regular activities. You're pouring a drink, you're drinking, you're chopping, you're washing utensils, you're washing your hands, etc. These are the types of things we can detect by adding like some deep learning technologies to the smartwatch signal. So we've deployed this is synthetic sensors now. We've deployed it on like residential, institutional, and commercial. What if you have multiple synthetic sensors in a home? Can they work together, right? Instead of just one in isolation. And it turns out that a sensor in this room can detect events in a sensor from another room as long as they're almost nearby. And you could use those two to basically help each other and improve the accuracies or help with robustness. And finally, sensors is being integrated into the city of Pittsburgh. So especially, most specifically the parking authority. So these guys are really interested in digitizing, getting real-time metrics on like parking usage. And I think they mentioned that it's the first time no one has ever done like surge pricing for parking before, because it's really hard to do that. But with sensors, they're hoping that they can actually implement that. So you get more foot traffic in urban areas that you want a lot of business to flourish, etc. There's a lot of more future work that I'm planning to explore. So things like differential privacy, plug-and-play sensing, where you don't have to train anything, and just plug and play, and the users can actually get the benefit out of it. And I'm also doing a project with Jeff Bigham's accessibility group, where we're actually using synthetic sensors to measure wheelchair basketball usage. So fatigue is a very important thing that a lot of these guys want to track. So if you put synthetic sensors on the wheels of the wheelchair, it turns out you can actually detect all these things like dribbling and if they're pushing or not. And it's actually really cool. Lastly, I just want to talk about broader impact. So there's lots of ways you can make broader impact. One of them in research is actually if you disseminate your work into the public. So I'm lucky enough that my work has been covered by a lot of press, like NPR, the New York Times, Wired Magazine, NBC, Bloomberg, and a lot of these work has been resonating a lot of people, and that comes in like millions of views on social media. And as a researcher, I feel very proud of that because it means my work is being disseminated out there into the world. I'd also like to say that I've open sourced the Viband kernel code that you guys just saw. So we're trying just to tweak to make sure everything is good to go, and then we're going to release that to the public and say, hey, you guys can actually take Viband yourself and hack all these watches and see what you can come up with. We've manufactured 500 of these synthetic sensor boards that you see. So we have 500 of these guys. We're actually sending it out to universities, and we're partnering with these guys because they also want to sense lots of different things in their environment. So this guy is also being out there into the world through inter-university deployment, not just within CMU, but lots of people want this. And actually, for me, that is really good. And finally, I want to say that synthetic sensors is spinning out as a startup. So that technology is being taken care of by lots of collaborations at CMU. And I'm very, very lucky for someone to pick that up and move it into commercialization. Wideband has been commercially licensed. I can't name the companies, but it's very rare for research to get a patent and then get licensed. So I'm glad to say that both Wideband and MSense have achieved that status. And Zensors is also spinning out as a startup. I'm actually a co-founder of that. And so this is part of the collaboration that we're doing with the city of Pittsburgh and, of course, all these other places like Costco and warehousing and medical places that want real-time analytics for their smart spaces. And that's it. I'd like to acknowledge all of my mentors and collaborators. There's a lot of them, but these are the people that were involved in the projects that I mentioned. And that's the end of my talk, and thank you very much for your time and attention. I'm now opening the floor for questions.
Super cool work. I was wondering, so you the demos are really impressive, right? Particularly synthetic sensors. How robust is the detection when you have multiple things going on, like in the kitchen, right? So sure, I can accurately detect the grinder and the stove turning on. What if the grinder is running, right? The exhaust is running, I'm cooking. What is running at the same time?
That's a good point. So I'm going to show you a demo of multiple devices running at the same time. So there's clever ways to do that machine learning wise. And so this part of the video where I actually go crazy and have multiple devices running at the same time. So here. Second order synthetic sensors. Okay, so here's a mini kitchen setup. What's happening here is you turn on the light, you see the activation over here. So I say the light is turning on. You turn on the stove and you can detect that that the stove is running at the same time. So you see the other activation. These are all running simultaneously. You turn on the vacuum and it says that, hey, I can detect the vacuum. And you turn on the microwave, it can detect the microwave. Oh, you turn on the blender, it can detect the blender. So there's ways in machine learning to do this because you can actually, if the signatures are really unique, you can use some form of masking or have multiple classifiers just focusing on that thing that they want to sense. And you can use those as an ensemble method to basically detect multiple events. Of course, it depends on the type of the signal. So if the signals are not overlapping, so let's say it's using vibration and the other one is just using sound, then you can have multiple of them together. But if they're clashing, it's really tough to go over a crosstalk, but there's clever ways where you can prevent that. But the point I'm making is it's possible. You just have to be clever. A, you have to know your signals, and B, you have to figure out how to make it in a way that is workable and good for a user experience. But it is possible. Steven.
Yeah, can you talk a little bit more about the decision to remove the camera from the synthetic sensors? Was it a technical decision? Was it a privacy concern decision?
So it was mostly just from it. We just wanted to see how far we can push the idea of not having a camera, but still being able to sense things around. So I would almost just call it as a research vehicle. So a lot of people think that, oh, why do you have all these different sensors and you're not using X amount of them? We're just saying, hey, this is just a technical vehicle. We want to say we have all these different sensors and see which ones work really well and which ones can be useful. And so what we've learned is that there's things you can do without a camera, but they're complementary. I feel like sensors and synthetic sensors are complementary. You're looking at different events at very particular angles, but mostly the reason why we didn't use the camera was for just see how far we could go. Yeah, that's basically where the motivation behind it was. Walter?
So do you have enough sensitivity, kind of going back to the multiple devices at once, do you have enough sensitivity in the signal to start doing things like triangulation? Can you use multiple synthetic sensors to actually figure out
that's a great,
over there and over there?
Yeah, that's a great point. So because you get the raw signal, so you can get the amplitude of the the sensor from here, sensor from here, sensor from here, and you could basically, again, triangulation, you could do the radius of like how far this thing is. That's just the acoustic signal, right? But you can use other signals like EMI, because these guys also detect EMI. So you can use them to figure out where approximately these sensors are relative to each other, because the EMI sensors will kind of overlap, actually. The other thing you could do is if you like do this on the floor, the sensors get activated depending on like where the source is,
Kind of a
right?
clapboard.
Yeah. And the other cool thing is, what I've learned is that you can do signal correlation. So if you have synthetic sensors that are listening, they're sensitive to vibration, you also have a phone that has an accelerometer. You also have a watch that has an accelerometer. So if I walk, I create this very specific accelerometer pattern. These guys also can detect that accelerometer pattern. So you can almost like correlate all these signals together to A, infer like where is that event happening, and B, who is causing that event. Right? There's all these different things you can do just by having these like rich signal sources. Yeah.
How long does it take to train the sensors, and like, do you have to retrain it every time you might move?
Is this which project is the
For
sensor?
the last one, yeah.
The synthetic sensors.
Yeah.
Okay, that's a great point. So more data is always good. So in the demo that you've seen, I only gave it like 200 instances. So roughly about 5 to 10 seconds of demonstration, and it's able to generalize those different patterns just by 10 seconds of demonstration. But of course, if you put like a really loud AC in front of it and it hasn't learned all those other events, it will fail. So you have to give it more and more data to know that, hey, there's a new event that's coming in, I have never seen this before, can you help me? So there's all these different ways that you can improve the system through like reinforcement or anything like that. But so far, what you've seen, 200 instances of data was enough to show that functionality. Michael.
Yeah, thanks, Gierad. This is nice. There's lots of components in your talk that I really like. It's really visual and lots of applications. And so I was wondering whether you could reflect a little bit and like give some advice. Right? My research team is currently working on WISP papers, and we are trying to look for really cool applications. And I think you have a really good sense for exploring a design space and picking compelling examples. So do you have like a specific method behind, like, do you just go through the kitchen randomly, or like, do you have a method of coming up with good applications?
So one of my rules is that if you have a technology and you're trying to tell the world, hey, this is really empowering, this is really good, your job as the researcher is to tease apart the space. And so your job is to make your examples as far away as possible so that you basically plop like a little area of where the space can be, right? But if you put two applications close together, you're just basically mining that part. But if the applications are like this, then you basically say, hey, this is what's possible. So that's one way for me to think about how these applications can be done. The other one is just like taste. Like, I don't know how you acquire it, but you just like, I don't know, you just do it. You just do it. Yeah. And the other is like,
Okay, good.
the other is like, you almost have to like envision yourself like in the future and saying, you know what, that is actually going to be useful, and that would be like a killer application to demonstrate that it only works. You can never have this without this system, right? So that's also another way for me to think
Take
about it.
sensors, just to follow up. So was it from the beginning a thing that you want to look at a parking lot, or did you have this application in mind from the beginning, or was it like a set of experiments that led you to this is the most compelling application?
So it always never goes the other way around. You always have like, I have this technology, what can I do with it? And I think that's where you start. And then it's like, you sleep on it, you wake up, it's like, oh, you know what? There's this other thing. And I think when I work, I try not to context switch between different projects, because what I've learned is that if you focus like 6 weeks thinking only on one project, there's a lot that you could come up with by just focusing on that one thing for 6 weeks. But I also do a lot of projects, so I'm almost like a spotlight. So I focus on this, and that's all I do for 6 weeks. I think about it as much as I can, and then when I'm ready to go, I move to the next one, like a spotlight. And so I think that's what allows you to think deeply into these different spaces.
Okay, thanks for the advice.
Yeah. We can chat more offline too.
Just want to do one thing at a time. Become a professor is impossible.
One more quick question.
One in the back.
So
you'd mentioned that you were able to create a library of information for, I believe it was the ARM project?
The acoustic, yeah, the
Are you
signatures.
able to collect this information and kind of model it for the sensors so that you, or does the user have to then like try every appliance in their kitchen to test?
It's a good question. So my vision is that it's kind of like you have a repository that people contribute to. So, you know, everyone has different drills, everyone has different refrigerators, but you have to build a system of like signatures. Basically, it's like, oh, you know, I want to register this drill into like the MSense repository or something like that, and then you have this pattern. And so I imagine people just like contributing to that type of repository. That could be one. You can also imagine a company that has lots of different products creating this library or repository of different things. And that's just EMI signals. There's all these other, I'm going to hint on a future project. There's all these other things that have repositories of signals. So one of the really cool thing that I'm excited about right now is sound effects. Turns out that there's a ton of sound effects out there that people have been accumulating over time. So like the BBC has been collecting sound effects since the 1950s, right? So you have this library of CDs that you can learn from in terms of like sounds, right? And the music industry has like lots of sound effects to make sound effects. And so you can actually learn from those guys to see and have this repository of things. And what I really appreciate about that is the archives people almost like has a new sense of purpose now, because you can train, you have archives of these different collections and you can use those for deep learning, which is actually very data hungry. So you can have these archives of different things, and now you can train like models to learn like different sounds, for example, from like since the 1950s, like what are the computer sounds, or the typing sounds, or all these different things, and feed that into like a deep learning model, and then you have like a huge repository. I wish I could show you, but I have a project that is like very similar to that, and it's actually quite cool. No training needed, because you're just basically using archives from the past to feed your data. It actually worked quite well.
Thanks, Gierad, again.